Today we're going to look at Boolean algebras. Okay, now what you need to understand is that a Boolean algebra is more general than a Boolean expression. Boolean expressions, which we looked at last time, consisted of and, or, and not, and can only take on values of 0 and 1. Now, what's a Boolean algebra? Well, a Boolean algebra is just an arbitrary set S that includes 0 and 1, but it can have other stuff in it. And because of that it can have more things other than 0 and 1, means it takes more than just a table to prove that two things are equivalent. Okay, so a Boolean algebra is a set. It includes 0 and 1. It includes two binary operations, plus and dot. Now, I call them plus and dot. They look like addition and multiplication, but I need to warn you that they don't always act like addition and multiplication. Okay, so two binary operations and one unary operation called complement. And those operations are going to satisfy the axioms that follow. The bottom line is, if you want to prove something is true in a Boolean algebra, you have to do it using the axioms, because that's essentially the only thing we know. All right? So, just as in algebra, dot is oftentimes written x times y as opposed to x dot y. We get lazy. And like I said, I warned you, it doesn't always act like multiplication and addition. 1 and 0 are just symbols for things in S that act like we state below in the axioms. So again, you should be warned, they are not actually 1 and 0 that we use in algebra. Although some properties are the same, all properties are not. There is also an order of operation where it's understood that I do dot before I do plus. Okay, in the absence of any parentheses. Okay, so we're going to talk about the axioms, and you're going to notice that the axioms come in pairs. If we were in regular class, I would make you memorize these axioms and be able to use them. I still encourage you to do so, even though I'm not going to be able to check it online. So how can you remember these axioms? Well, I have a little mnemonic device that might help. The sentence, all cars drive in cities. The first letter in each word corresponds to a pair of axioms. So A corresponds to the associative axioms. Get it? C, the commutative axioms. D, the distributive axioms, etc. Now, some of these axioms you might have seen back in algebra. Okay, the other thing I want you to notice is that the axioms come in pairs. There's two of them. And we say one pair is the dual statement of the other. Now, what is a dual statement? Well, a dual statement is obtained by switching ones and zeros and pluses and dots while keeping the complement the same. Okay, so let me explain what I mean. Let's go down to the associative axioms. We have two of them. If I start with this statement, the way I make its dual is everywhere I see a plus, I replace it with a dot. Everywhere I see a dot, I would replace it with a plus. And if it had a 1 in there, I would replace it with a 0 and vice versa, right? So the dual statement of this is this. Notice you have to do x dot y just like you have to do x plus y. So I would encourage you to put parentheses in before you try to figure out what the dual is. The dual of x plus y equals y plus x, again, everywhere I see a plus, I replace with a dot, is x dot y equal y dot x, etc. All right? So that's what a dual means. Now let's look at the axioms. The associative axioms, if you saw the associative property in algebra, it's exactly that. What does that say? That it doesn't matter how you group things if it's always the same operation. So x plus y plus z is the same as x plus y plus z, and the same thing is true for dot. The commutative axioms, we assume that what? X plus y is always y plus x. So it doesn't matter which order you do it, just like x dot y is the same as y dot x. All right? That's the commutative axiom. The distributive axiom is, well, you remember the distributive property? It said x dot y plus z is x dot y plus x dot z. Well, that one you remember back in algebra. But we have another distributive axiom in a Boolean algebra that's not true in our regular college algebra sense. And that's gotten by, again, everywhere I see a dot, I replace it with a plus and vice versa. And so what we get is x plus y dot z is what? X plus y dot x plus z. Now that is a property that is not true in college algebra, but is true in a Boolean algebra. And what that means is we get some funny results. Okay, some surprising results. Okay, the next is set is the identity axioms, which you're going to recognize. X plus 0 is x. You probably believe that. Remember though, 0 isn't really the 0 we knew back in algebra, but it seems to work like it here. And what's its dual? Well, everywhere I see a plus, I replace it with dot. Everywhere I see a 0, I replace it with 1. So what's its dual statement? X dot 1 equals x. Again, not a surprising result. And finally, we have the complement axioms. Now, what are the complement axioms? And the answer is a complement of x. Remember, I had a unary operator. Look all the way up here at the top. A unary operator said the complement of something. Okay, so the complement of x is an element that works like this. X complement add x is 1, and x complement times x is 0. Again, something that you don't see in college algebra, but is true in a Boolean algebra. All right, so these are the 5 axioms of a Boolean algebra. In other words, they're the only things that I assume to be true. Okay, so if I have a Boolean algebra, here are the 5 things I assume to be true. Remember, axioms are something you assume. You don't prove it. You keep that set of axioms down to a minimum. They have to be logically consistent. And they really define your mathematical system. Now, your author calls these things laws. I have a problem with that because he also calls some other truths laws. Okay, but the other 6 laws are not axioms. In fact, we use the axioms to prove that they are true. That's why I distinguish between what I call an axiom, of which there are these 5 pairs, and laws, which can be proven from the axioms. All right, so that's where I part ways a little bit with your author. Okay, axioms are assumed truths, and anything I'm going to prove about a Boolean algebra can be proven by going back to these set of axioms. All right, so that is the beginning of what a Boolean algebra is, right? It's a set with 0 and 1 in it, 2 binary operations and 1 unary operation, and those operations work like this. The thing again to remember is a Boolean algebra can have other values than 0 or 1, which means I can't just run a table of all possible outcomes. Hence, I actually have to make arguments. Well, I hope everyone is doing all right. Keep safe, work hard, and bye.